the difference between complex functions and real functions, which is in real analysis, and sometimes in calculus actually, you learn about the existence of, most of you that have taken that class have learned that smooth does not mean analytic. This is like one of the really important facts about real functions, is that I pointed this out earlier, that it's possible to construct a function where you let the function approach the origin from one side and it's just identically equal to 0, right? So it's just going to be a piecewise function. So it's 0 when you are, so f of x is identically 0 when x is less than or equal to 0. And then you join it up with some sort of exponential function that has infinite derivatives and they're all equal to 0. So you can imagine that you can come up with a function that has this kind of behavior. So one way of doing that is you can take an exponential function, you can slide it down. Like you can basically fit this so that this asymptote works perfectly by translating a function that you already know. And you can make it so that this join agrees that this derivative here from both sides is 0 to every order, right? That every derivative of this function is 0 at 0. And so that would seem like it violates so this looks like, if we're in complex analysis, that looks like an infinitely differentiable function, right? This is differentiable in every neighborhood of 0. And the derivatives exist to all orders. And so if you pick some neighborhood here, every neighborhood around 0, every neighborhood, has the property that f is differentiable to all orders at 0. Because the derivative from the left and the derivative from the right agree with each other. It turns out to be the case this can't possibly have a power series, because not a power series centered at 0, because if it did, then half of it would be identically 0. So if this did have a power series centered at 0, so say you assert this function must have a Maclaurin series, and you think about what that would mean, in order for this thing to have a Maclaurin series, this thing would have to converge for all values of x in this little band of convergence, right? But that means that everything over here would mean that the function was identically 0. The power series on one side is identically 0, the power series on the other isn't, right? So if you use the right-hand side to find the power series coefficients and you plug the left-hand side in, these aren't zeros over here, these are numbers, right? So if you use the right-hand side, you get non-zero numbers for coefficients, and then it's not identically 0 on the left. And if you calculate the coefficients using the left-hand side, the coefficients turn out to be identically 0, and then it doesn't work on the right. So in real analysis, this is one of the big differences. Smooth functions, so smooth or C infinity functions, even with our beefed up version of differentiability at a neighborhood and not just a point, still aren't analytic. C infinity or smooth functions in real calculus aren't always analytic. So there is no power series that describes this function. And I actually was curious if anybody else can figure out why. What's going on here? Why can't this thing have a power series? What could go wrong? Well, what if it was analytic? What would that say? I mean, what would it need? What would we need to guarantee that it had a power series? I mean, we proved it, right? I guess what we would need it to be holomorphic, right? So like we haven't proved that yet, but Taylor's theorem says that if you're holomorphic, then you have a power series. Differentiable implies power series, right? Certain kind of differentiability. But that's a complex analysis theorem, and it says that holomorphic differentiable on some disk. And so what ends up happening here is if you restrict this function to the real axis, it looks smooth, but if you look at the complex derivatives, it falls apart. So this function is not complex differentiable, even though it's real smooth. It's a really smooth function. But in complex analysis, it's not, right? This is not a function that we would consider to be a holomorphic function. It's not differentiable, complex differentiable. And so we're asking more when we ask a function to be differentiable on a circle, on a disk, instead of just differentiable on a line. So it's worth keeping the examples like that in mind. Okay, so what I want to talk about today, besides the quiz that I tried to get to and I didn't because I was dealing with a million calculus students, so I apologize. They're in my backpack. I'll have them back by Monday. that's the old quiz. The new one I've got in my bag. It's just. I want to talk about inverse functions today. Let's talk about inverse functions. And I want to visit an old friend. And the old friend that I want to visit is y is equal to x squared. Let's look at f of x is equal to x squared. Is that function invertible?
No.
Why not?
Because it's one and negative one are the same thing.
Sure, okay, you learned that like a function is only invertible if it's 1-to-1, right? Every input corresponds to a unique output. So this function has the property that other than the special case of 0, every output corresponds to 2 unique inputs, right? So there's an x and there's a minus x, and x and minus x both correspond to the height x squared. Okay? And so you actually learn, well, this doesn't just have one inverse, it has 2. They don't ever tell you that's what's going on, but f inverse of x is equal to either minus the square root of x, or f inverse of x is equal to positive the square root of x, depending on how you've chosen your domain, right? These are the standard inverses of f. F has this inverse if you're over here, and it has a different inverse if you're over here. The complex analysis perspective is actually, this is just one function. It's one function with 2 pieces, right? So that it's what's called a multi-valued function. So if you want to like loosen up your idea of what a function can be, one way of thinking about f inverse is, well, if minus x gets sent to x squared, and also x gets sent to x squared, that's what f does, then you could think about f inverse as taking x squared and sending it both to x and minus x. So there's a way of viewing the function as what's called a multi-valued function. It's a 1-to-2 function. Every input produces 2 outputs. So the perspective here is to think of this as a multi-valued function. Now, we don't often do this, but it's a way of thinking about the function as containing both rules at the same time, right? That the inverse produces 2 values from each input value to completely characterize exactly what could produce x squared. Okay, so these things, these pieces, to use the language of complex analysis that was really secretly going in the background all the time. Yep.
Isn't that not technically a function?
That's why I put the word multi-valued in front, which modifies function.
Okay.
Yeah, so a multi-valued function is not a function.
Okay.
It's not, right? Because you're taking one input to multiple outputs. But it's still, you can define what this means as long as it's consistent about what it produces, right? This only ever, aside from the one magical point of 0, every input here produces 2 outputs in a controllable way, right? And what we do is, if we're using the language of complex analysis, we would call this a branch of the inverse of f of x is equal to x squared. The inverse has 2 branches. It's got a positive branch, and it has a negative branch. So here's the other branch. The inverse of f of x. And I have to tell you which branch we're working on. If I want to use this in practice, you may not remember the obnoxiousness of learning inverse functions the first time, but they absolutely make you write down the interval that you're working on so you can very carefully say what the inverse is that you're doing, right? So what we're going to do is we're going to take that idea and we're going to look at what that does with complex valued functions, like not f of x is equal to x squared, but f of z is equal to z squared. This is going to be our entrance to talking about inverse functions. So if I have f of z is equal to z squared, and I think about what this is doing from a polar decomposition, so f of r e to the I theta, I'm going to remind you guys that in a polar decomposition, we always think of the radius in complex analysis as being a positive number. We don't allow negative radii, and the reason is because we're always thinking about r as being the modulus of z. And the modulus of z is a distance, which means it's always positive. Okay, so this isn't like polar where they try to trick you in the earlier stuff. It's always, by convention, if I do a polar decomposition, the radius is positive. which means square roots of all orders will exist. Right? Nth roots will exist. Okay, so what does this do? This takes r e to the I theta and squares it. Distribute the square, r squared e to the I 2 theta. So what the z squared function does in the land of complex numbers is not only does it square the length, just like it does over here, but it also rotates the number as well, right? Because it doubles the argument. If this number was r e to the I theta, r squared might be here. R squared, so you've squared the radius and you've doubled the angle. This is theta, this is 2 theta. This is r, this is r squared. Right? So squaring is like it turns the inputs to outputs. Right? Doubling an angle means that you're rotating the point. Now, why doesn't it turn? I mean, really, secretly, this thing is z squared. Why don't those numbers get rotated? Because the argument's 0, and twice 0 is 0, right? Or if you like, what if it was 2 pi? What if you thought of this number right here as, you know, if you thought about the number 1 and you square it, what is the number 1 doing when you take its 2 pi argument and double it? Well, now you're at 4 pi, right? So regardless of how you choose the argument for that point, it rotates on top of itself. And the same thing here, no matter what you choose to have happen to -1, say, the square of -1 is just 1 because -1 squared is 1. Or if you like, actually, I don't even know why I said that. You can't do that. -1 is not equal to -1. -1 is equal to 1e to the I pi. So there is no such thing as -1. There's just 1e to the I pi. If you square that, you square the 1 and get 1, and you square the e to the I pi and you get e to the I 2 pi, which rotates you back around to 1. Yep.
So if you restrict this complex value function to only the real numbers, you'll just get
Regular old square.
But if you represented it in the complex line, we just get the half line going to.
Yeah, what's going to happen is this line maps directly onto this one.
Right.
Right. This is fixed by the function, and this like turns around and lands on top of it.
Right. Okay.
That's actually why it's 2 to 1, because you can imagine this radius is being rotated, but it's being rotated rigidly, and so it just lands where all the points land right on top of the points of the same radius, if that makes sense.
Sorry, what does it say the squared part?
There's just r. Sorry, I accidentally. That was just an r. Okay, so that's what squaring does. What should square rooting look like? Oh well. What should square rooting look like? Well, yeah, right. I mean, like if we think about the inverse, of z squared, it just undoes that process, right? So the inverse, if this is f, we would expect the inverse of f to root the radius and have the angle, or the argument. Argument. Remember, the argument is the theta, right? So that gives us our first notion of what the inverse of this should be. And if in the real line, if I just restrict it to real numbers, the inverse of f is just the square root of z. F of z is equal to root z. What should that do to a complex number? It should take the radius and square root it, and it should take the argument and divide it by 2. And that would undo what f of z is equal to z squared does, right? Which is root r e to the I theta over 2. So this is called the principal branch of the square root function. It's the principal branch of the square root function because this is the one that corresponds to like the positive square root of x when you take the plus or minus part, right? You think of this as the positive part. Unfortunately, this thing is 2 to 1. As a complex function, this is still 2 to 1. f of z is equal to z squared sends two different numbers to the same output. So if you put in r e to the I theta and you squared it and get out r e to the I theta, like 2 theta, can you think of another number that lands at the same point? A different number? This is going to require thinking a little bit about the angle of the function here.
Pi to theta.
So if we also took f of r e to the I theta plus pi, let me make it more clearly, I theta plus pi, which would be r squared e to the 2I theta plus pi, which would be r squared e to the I 2 theta plus 2 pi, and e to the I 2 pi is 1. R squared e to the I 2 theta, e to the I 2 pi, this is 1. And those numbers are distinct from each other, right? They differ by pi radians. If you want to think graphically, what's going on here is that if you squared this number and you square this number with the same radius, you land in the same spot. We already see that when we're right here, right? When we're at 1 and minus 1, squaring 1 gets us back to 1, and squaring minus 1 also gets us to 1. So these two outputs that are pi radian, that are on this diameter that cuts through, each one of those inputs corresponds to the same output. So this is still a 2-to-1 function. This is 2-to-1. 2 inputs to 1 output. And that should make you think that just like in the real case, that function, this inverse, really should be thought of as having 2 branches. One that reproduces this number when you undo it. If you take this input back to this part, right? Undoing a square and landing here is one branch. But I should also be able to undo a square and land over at this one too. I want to be able to undo both parts, the plus root x and the minus root x. So I need to define both parts of the inverse of f of z is equal to z squared. And so what I can do is just make it do that. So this is what the other branch looks like. So we have f inverse of z is equal to, so this is the principal branch, root r e to the I theta over 2 is the principal branch. I don't know why I put a dot over the r. And then the other branch looks like this. F of z inverse is equal to root r e to the I theta over 2 plus pi. It gives you the other point with the same radius but rotated by pi radians away. You can test this out, by the way, if you want to make sure that both one on this branch produces a 1 and one on this branch produces a negative 1. So this really is like the minus root x branch, and this is the positive root x branch, is the way of thinking about it. And so inverses in complex analysis are complicated because you have to say which inverse, what the domain or what the range of the inverse you're talking about actually is. Which inverse? You have to pick a branch. Am I recovering all of these points or am I recovering all of these? Because yeah, like you said, it's not a function, so they're going to be, yep.
Is there a name for the branch that's not the principal branch, or do you just say it's?
I would say that it's a branch. I mean, in the case of the square root, there's only 2 branches.
All right, but there can be any.
In fact, the next example we're going to do is going to have infinite branches.
Is picking the primary or the principal branch arbitrary?
What's that?
Is picking the.
We always pick the principal branch so that the angles that fall out fall on the principal branch of the argument. So minus pi to pi. That's really what we're after here, right?
Yeah.
Okay. It's okay so far? This isn't so bad, right? This is just like plus or minus square root of x. I'm going to pick which inverse by deciding where I want the outputs to map. Okay. Okay, so what's the most important inverse function in the entire universe?
ln.
Yeah, ln. Exactly right. Why is that the most important inverse in the entire universe? It's the inverse of e to the x. Okay, so what about f of z is equal to e to the z. We're not going to get very far in analysis if e to the z doesn't have an inverse. Right? That's going to be a real problem. Okay. So what we're going to try to do is we're going to try to discover a formula for what the logarithm, we're going to call it a logarithm, and it's going to have the properties of a logarithm. We're going to try to discover a formula for what that must be. So we're going to start with the easy case. If z is a positive real number, what can you say about the function? Okay, so I'm going to bracket this for just a second because I'm going to start by saying, let's write down the inverse. F inverse of f of z, which is f inverse of e to the z is equal to z. Let's call the function that does that log. Seems like a reasonable thing to call it. So f inverse of z is equal to log z. Capital log because we're defining the principal branch of the log right now. There's a choice that we're going to need to make. So whatever it is, whatever the inverse of e to the z is, we're just going to call it log. I don't even know it exists yet, but if it does, it's called the log. What can I say about the function logarithm of z if z is a positive real number? Yep.
We know it.
Do you? Why?
If y equals e to the z, then log y equals z.
Yeah, the idea here is that if you had y is equal to e to the x, where x is some positive real number, I know the name of the inverse of that function, which is ln, right? Then we would say x is equal to the natural log of y. So why is this hold, by the way? Why am I allowed to say that log z is equal to the natural log of z? Because I'm going to say that. And that's a fancy name we want to invoke. Here, you want proof? Here's a little proof. Why is this? So this is equal to the natural log of z when z is a positive real number. By what theorem? It's the extension theorem. The extension theorem says that if these two things agree on the real numbers, then they're the same thing, right? That's what the extension theorem says. If we have a formula and it's defined on real numbers, then it just works. It's the same formula. Complex numbers restricted to the real line, the functions agree with each other. Because e to the z restricted to the real line is e to the x. That's a real function. The inverse of the real function is log y. So the inverse function restricted to the real line must be the natural log of z. You can walk through the chain of logic here if you want. But essentially, it's an extension theorem argument. Okay, so it's log z if z is a positive real number. That's not surprising. I would hope, anyway. How the hell are we going to find a formula for this? The answer is, oh no. We don't even know what even the possible form of this thing could be. I could write down a Taylor series and pray, I suppose. But I don't even know the formula. How am I going to compute derivative? Right? Plus, we haven't proved Taylor's theorem yet, so we don't even know it holds. So what we're going to do is we're going to say, okay, whatever the log of z is, it must have a real and an imaginary part. So let's say that the log of z is equal to u of z plus I times v of z. I don't know what they are, but it certainly must have a real part and an imaginary part. That's another way of writing down a complex function, is in terms of its real and imaginary parts. And u and v are real functions, right? Okay, well, what do we know about the log of z? It should be the case that e raised to the log of z is equal to z. That had better be true. So that means that e to the u of z plus I v of z had better be equal to z. Just replacing the log of z with its real and imaginary part representation. But that means that e to the u of z times e to the I v of z must be equal to z. Oh, that's starting to look familiar. Let's write the polar representation of z on the other side of this equation. E to the u of z times e to the I v of z is equal to the modulus of z times e to the I argument of z. This is the polar representation of a complex number, right? It's the length of the complex number times e to the I, and the argument here, which is the angle that it makes with the positive axis. I've been calling this theta, but remember, that's what argz does, right? Argz eats a complex number and spits out the angle between minus pi and pi that tells you what the angle that it sits at is. All right, are there questions about what I've done here? All I did was I took z and I replaced it with its polar representation. Is that okay? And the reason that I used capital A argument was because I called this capital L log. Oh, well, this is easy then, right? Two complex numbers are equal. So when I look at this, I think, oh, it should be the case that e to the u of z is equal to the modulus of z. Because the radius and the radius, those are both radius functions, right? I mean, this is e to a real function. This is real. And this is e to the I times something that, e to the I something, that's an angle. So it must also be the case that v of z is argz. All I'm doing here is I'm looking at the left side and right side and comparing. This bit must be that bit because that's a real exponential. So the real exponential piece and the real exponential piece have to be equal. And this piece are complex exponential parts, and they must be equal. Well, I can finish this now. That means if e to a real, remember, u of z is real, right? And if I have e to a real number, I can take its regular old natural log. It's e to u of z is a real function. So this says that u of z is equal to the natural log of the length of z. And v of z is equal to the argument of z. And now we know what the log is. The natural log, the log is equal to u of z plus iv of z. So that means we've got a definition. Log z, complex logarithm, principal branch, is equal to the real natural log of the length of z. That's defined because modulus of z is a real number, plus I times the argument of z. And that weird looking thing, that's what log is defined to be in complex analysis. Let's see if it satisfies our requirements. How about we take log of e to the 2? Well, what is log of e to the 2? I take e to the 2 and I rewrite it. I rewrite it in its length times e to the I argument form. So I write the polar representation of the number. E to the 2 times e to the I 0. And so that's a real number, right? Positive real number. So what does log of e to the 2 say I'm supposed to do? It says I'm supposed to take that number and take its natural log, so it's the natural log of the length of that thing. The natural log of e squared plus I times the argument of z, which is the natural log of e squared plus I times 0. Which is the natural log of e squared, which is 2. Oh, it works! At least for that number. Yep.
Would you care about different bases for your capital log?
Okay. What do you mean?
Would it be defined the same, but instead of natural log with z, you'd have log
You never work in any other logarithm.
and you don't care?
Yeah.
You don't care.
Yeah, I mean, the thing is, like, if you wanted to do that, you could re-express this with different bases just by using the representation trick over here.
Got it.
Right? It won't change that's not going to actually change the argument of a number, right? The representation of the radius will change what the size of the radius is, but it shouldn't change the angle.
Sure, okay, yeah.
Now, what can change here, let's actually do a more complicated example real quick to make sure that this thing actually does what we want it to do. What's the logarithm of, let's say, e to the, let's do, how about 1 plus I? Well, I can't do logarithms in rectangular coordinates. I have to shift to polar. So I rewrite this as the log of root 2 e to the I pi over 4, I think. And what does log say to do? It says you're supposed to take the natural log of the radius and then add it to I times the argument. So this is the natural log of root z plus I times pi over 4. Okay, so why is it that? This is a good question. Why is it this? Why do we define the log this way? Well, what's the inverse of taking the log? So if I take that number and I take e and I raise it to that exponent, I should recover the original number, right? Log and exponentiation with a base of e are supposed to be inverse functions. So let's check this, and let's compute e raised to the natural log of the square root of 2 plus I pi over 4, and make sure that we get the original number back again. Well, e to the log root 2 can be broken off into its own piece, and then I get an e to the I pi over 4. So I take the exponent, I chop it up with multiplication. This is real, so e and log cancel. And then the e to the I pi over 4 trick is to replace it with cosine plus I sine. And here's where I remind you guys that you're obligated by all of your training to have the unit circle permanently tattooed on either your brain or some visible part of your body. So this is root 2 times the cosine of pi over 4, which is root 2 over 2, plus I times the sine of pi over 4, which is root 2 over 2, and you get back 1 plus I. Oh, sweet, it works! This is why this extra argument piece is in here, is to pick up this rotation that happens, right? So this I argument piece holds the complex rotation, that information, and this part with the natural log of the radius holds what happened to the length of the complex number. Okay. How many branches does this function have?
Well, you said before it was
Well, let's think about all the numbers that e to the z sends someplace, right? Let's just look at all the numbers that e to the z. Let's think about all the numbers that e to the z sends to 1. How many numbers does e to the z send to 1? Well, certainly it's the case that e to the 0 is 1. And also, e to the I 2 pi, that's equal to 1. Oh, and also e to the I 4 pi is 1, and also e to the minus I 2 pi is 1. Oh, crap. So it's 0, and plus or minus 2 pi I, and plus or minus 4 pi I, and plus or minus 6 pi I. So e to the z is an infinite to 1 function. There's an infinite number of complex numbers that e to the z sends to 1. So this is infinity to 1. So how many branches does the inverse have? Infinity. You have to say, which set of values are you trying to land in? Do you want the principal branch between minus pi and pi? Do you want the next branch between pi and 3 pi? Or the next branch between 3 pi and 5 pi? You have to pick which band of values that you want this to be defined on. And the way that you adjust it is you define something called little log z, which is the natural log of z plus I times little arg z. And remember, little arg z is that it's like the angle plus some factor of 2 pi, some multiple of 2 pi. So here you can think plus the natural log of the absolute value of z plus I times, I shouldn't even say that. It's like arg z is equal to arg z plus 2 pi k for some integer k. These are the other values the argument can take, right? The other bands of admissible angles that we allow. So it's your responsibility, if you're going to work with exponentials and logarithms, that you either work on the principal branch, which that's what you'll be working on unless it's otherwise stated, or you pick. The last thing I want to ask is, where is this function analytic? E to the z is entire. It's good everywhere. What about log? Well, are there problems with logarithms? Are there problems with logarithms in real calculus? Where is it bad? 0. Anywhere else? Any negative number, right? So ln of z was bad at z is equal to 0. Oh, sorry, ln of x was bad for all values of x less than or equal to 0. Do you remember that I pointed out that the arg function that we define this in terms of has a branch cut where if we approach the angles from one side, they look like minus pi, but if we approach from the other, they look like positive pi, so there's a discontinuity there. That discontinuity, because the log is defined in terms of the argument, it has the same discontinuity. So log z, which is equal to ln, this will never be a problem because you're only taking natural log of positive numbers. Oh, and 0 is bad. ln has no idea what to do with 0. Because there's an arg z in here, this function is analytic everywhere except all values of z that are less than or equal to 0. Now, in complex analysis, it's typical when we write an inequality like this, we're telling you that it's a real number, right? Complex numbers don't satisfy inequalities. So if I write something like this down, I mean the imaginary real line. So the place where a natural log of z is good is everywhere but there. Everywhere else you can find a power series, it's infinitely differentiable, it's totally well behaved, but if you run across this, bad things happen. Okay, so I'm going to yep.
Even though it's defined for z's less than 0?
It's not, no, it's not defined. It can't be, right? Because it's defined, but it's not analytic, right? It has a value here, but when we say analytic, remember what we mean is we can find a little circle where this thing is well behaved at any point. So the problem is if I choose a point on the real axis, the values on this side and the values on this side have this horrible jump discontinuity that happens between them. And so it can't have a power series there because of that jump discontinuity. Right? But other than that, things are cool. Anyway, if you want to, so I'm not going to talk about Riemann surfaces right now, but if you want to, we're going to do that in the second quarter mostly. But if you want to read about the Riemann surfaces, he has a very nice description of how this links up with Riemann surfaces in the textbook. I think it's chapter 1.3. All right, so I'm going to hand out this quiz. You guys get grinding, and then you can leave for your weekend. I'm actually going to walk. I have a sheet I'm going to walk around with and see that you guys have done your homework, I guess. Maybe when you're finished, you can turn it in. I'll take a look at it. What's that? Huh?
Do you leave like homework on the desk?
Yeah, whatever. You can assert it however you want. You can just come talk to me when you leave and show me your homework. I'm not going to be very thorough about checking it. Yeah. All right, here we go. Get started. Step away. Should be no surprises. Do your work. Tell me what's going on. Yes. Here you go. There you go. Oh, control factors in assembly. That sounds lovely. Right here, you hand them out. Hand them out. Pass them this way. Here's some for you. You guys have those and pass them away. Here we go. Chaos mode. And you, everybody, board.